Good afternoon from the SETI Institute in downtown Mountain View, California. My name is Simon Steele. I'm the Senior Director of Education here at the SETI Institute. And this is our holiday edition, coming to the end of December. And my guest today is Dr. Franck Marchis, who's the Senior Planetary Astronomer at the Institute. And we are going to talk about Hygiea and its ongoing identity crisis and what we mean by that. So we're going to have a chat about this object. We're going to find out a little bit about it. And if you do have any questions at all, please do send a message on Facebook, and we'll try and answer as many as we can. So I suppose we're going to start off by asking, what is Hygiea?
So Hygiea is one of the 700,000 asteroids that we know in our solar system. Hygiea is an interesting one because it's an asteroid which is in a main belt, so between Mars and Jupiter orbit, and it's one of the largest asteroids. It's number 10. It means that it's been the 10th one discovered. It was discovered in 1850, around. But it's a fourth one in size. It's one of the largest one. And surprisingly, we didn't know much about this body. We knew its orbit. We have a rough idea of its size, but we don't know much about its shape, and we have never taken a picture of it.
Okay.
Because those asteroids are so far away from us. This one is roughly 3 AU, 3 times the distance to the Earth's sun.
Okay.
That when you observe it with a normal telescope, you will see just a tiny dot.
Okay.
You're not going to be able to see any details on the surface.
So with putting this into context, we of course, a lot of people know the structure of the solar system, but we have the inner rocky planets. So we go to Mars, which is about 1.5 times further away from the sun than the Earth is. And then there's a gap, and then you get the start of the giant planets. We've got Jupiter, which is about 5 times the Earth-Sun distance. And between them is this belt, this asteroid belt of hundreds of thousands of lumps of rock.
Yes.
Some of which are the size of,
The
houses, and some of them are huge. Ceres is
1,000 kilometers
planet,
roughly,
yeah. And Hygiea, which is the fourth biggest, roughly the size of Arizona, if you want to, is about 400 or so kilometers across, is it?
Yes.
Okay.
Roughly.
Okay. And where did all this stuff come from? Well, why is this?
So
what is all this junk?
Those are basically, we think, remnant of larger body that collided, and the result of this collision is fragments. So those are fragments, and those fragments stay there because of the gravitational effect of Jupiter, and they never managed to accrete to form a bigger planet as well because of Jupiter gravitational effect. It's a very complex dynamic we have in this environment because there is Jupiter, Saturn, which have gravitational effect on this area, and those bodies don't really truly have purely what we call Keplerian orbit. They orbit around the sun, that's true, but they're also slightly perturbed by the presence of those large planets.
Okay.
So they really never managed to accrete again to form a bigger planet.
So Jupiter is throwing its weight around in that sort of part of the solar system and not allowing anything to sort of settle down to make another planet. The king of the planets is exerting his will. Yes. Yeah. Okay. Well, let's zoom in a little bit on Hygiea. First of all, this is a small body on astronomical scales. It's very, very difficult to see, as you say. So what techniques have you had to employ to actually take a look at this object?
So if you want to see a body like this, there is multiple ways. One way is to send a spacecraft to visit the body. It will take years and a lot of money to be able to do this, because missions like a Discovery class mission of NASA costs $450 million, for instance, to give you a scale. And it takes years to make those missions. Another way to send a space telescope, because in this case you can use the large aperture telescope and get kind of an image of a good quality image, and you're above the atmosphere. The third way, which is the one we use, is to use a large aperture telescope, the VLT, which is located in Chile, in the northern part of Chile, in the desert of Atacama, and its adaptive optics system. Okay. So adaptive optics, it's a technology that basically brought me to astronomy. It's a technology which allows to correct in real time the effect of the atmospheric turbulences. So you get a resolution, meaning the image quality, like if your telescope were in space.
Okay.
So you truly take advantage of the large aperture telescope to see details which correspond to this detail that a 8-meter class telescope in space will see.
Okay, so you need to see the small body. You need a very large telescope, and in fact, you're using the very large telescope down in the Atacama Desert, where you're at quite high altitude, so you get a good clear sky anyway.
Clear sky.
But that's not enough. You need to go a step further. So you've got a huge telescope. This thing is still small. So you take this next step, which is this adaptive optics. So tell us about the adaptive optics magic.
So the adaptive optic magic is not really truly magic. It's basically a combination of electronics and photonics. So it consists to correct the atmospheric turbulences by using small mirrors, which bend. And they bend such as they correct the effect of the atmosphere. The atmosphere above our planet, above us, is not perfectly stable. The atmosphere moves. And you see that if you look at stars, the twinkling of the star is due in fact to the presence of the atmosphere. If you go to space, you will not see that. You will see the star stay, the brightness of the star is the same, will not change. But because of the atmosphere, there is this motion, this slight motion and perturbation. This effect is visible if you look up from the bottom of a swimming pool.
Somebody said the astronomy from the ground is like ornithology, bird watching from the bottom of a swimming pool. It's the same sort of effect. Everything is blurred.
Everything is blurred. In fact, you don't realize that, but everything is blurred because of the atmosphere. But when you start building large aperture telescope, you realize that in fact the image quality of a 20-centimeter telescope is the same as the 8-meter class telescope. So to correct this effect, we invented adaptive optics. And adaptive optics got invented, went into telescope in 2000. When I finished my PhD, that was basically the time we have adaptive optics systems almost everywhere. And now they're getting better. Better in a way that they correct better, and they also correct at shorter wavelength. So in the past, adaptive optic system were working only in what we call the near-infrared area, so the long wavelength range, so that we cannot see with the human eye. But now adaptive optics also work in the visible, and that's truly what we use. We use the first visible adaptive optic system called ZIMPOL, available on the VLT.
Okay.
And ZIMPOL gave us the resolution invisible of an 8-meter class telescope in space.
Wow.
And using ZIMPOL, you can basically see details which are small, very small in angular resolution. So you can start seeing the surface of an asteroid, the shape, and see craters as well.
That is amazing. Just going to call out to some people here, and then we're going to take a look at Hygiea. People listening in from Kurdistan, from the UK, Australia, Brazil, Belfast, Spain, Louisiana, Benidorm, Orléans, France, and New Jersey. So welcome from around the world. Okay, now let's take a look at this asteroid.
So I have a picture here. Can we show my screen? Yeah. So those are 4 pictures of several asteroids we observe using the ZIMPOL instrument.
And these are the 4 of the 700,000 in the asteroid belt. These are the biggies, and this is pretty much all the mass of the asteroid belt.
I should mention that the part of our program, the PI is in Marseille. His name is Pierre Vernassa. The program we elaborated is to observe 38 large main-belt asteroids, and those are pictures of 4 of them that we collected. We have more coming, of course. But one of them you may have noticed, that's Ceres. Ceres is very known because it's very circular, spherical. It has this white spot here. This is Pallas, and you can see craters if you look carefully. And this is Vesta. Vesta has been visited by the Dawn mission.
Now Vesta and Ceres, we had the Dawn mission, didn't we?
Yes.
It did an orbit of Vesta, and then after a while it left. It was an ion-powered spacecraft, I seem to remember.
So for
and
those,
then went off to Ceres, which is and where it is now.
Yeah, for those 2 bodies, we have now a comparison ground and spacecraft thanks to this mission. So if you look at Vesta, you will see Vesta has a lot of craters and also this kind of impact basin, we call that here, called Rhea Silvia. So Vesta has been bombarded by a lot of asteroids and even fragmented. A piece of Vesta went off, basically, the
now
2000 part.
That looks more potato-shaped. That is not a sphere.
That's not a sphere.
And that's obvious from that image. Whereas Ceres, if we have a look at that, if you didn't know the scale, could be any planet.
Any planet, Mars would be more or less the same sphericity. And then you have Hygiea. So that's one of the first pictures we took, in fact. So something remarkable for this body, which is relatively small in diameter, 200 kilometers, is the shape. It's very, it's not spherical, it's spheroidal, we call this. And this spheroidal as we expect it to be, considering the size and the spin. Okay. Because if a body spin, and knowing its size, if the body has no what we call cohesion strengths, if it's made of very small fragment, it will take this equilibrium shape. And that's the shape of Hygiea. Okay. So it's very close to the equilibrium shape.
Now, when we look at, we've seen a lot of asteroids through the missions that have flown through the asteroid belt, and some, have either passing through, going like Galileo on the way to Jupiter and so on. They're mostly potato-shaped, if there is a potato shape, because they're all different shapes. But they're certainly not spherical. They're stretched out. They shape like sort of skittles. They're these sorts of things. So there's a distinction here that you're bringing out.
There is different type of potato shape.
Yes.
There is a potato shape due to the fact of impacts on the asteroids and fragmentation and the fact that a piece of the asteroid has been cut off. And there is a potato shape which is due to the spin of the body, considering that it's behaving like a liquid. And that's basically what we have for Hygiea.
Okay.
And what we were very surprised, because in the case of Hygiea, we know it's the large member of what we call a collisional family. This is something interesting. You need to understand, as I mentioned, that the reason we have so many asteroids in the main belt is because they have encounters and fragmentation and so on. And we know that in the past, the main belt had very large bodies, like 200, 300 kilometer diameter bodies. And those were basically disrupted, destroyed during impacts. Okay. And if you look at those asteroids, if you look at the color and the orbit, and go back in time, you will see that you can see that they're coming from the same body. So if I display on the screen the orbit of those fragments, and I go back on time, considering all the perturbation introduced by Jupiter and Saturn, I will see that suddenly this spread amount of fragments, there is like 7,000 of them known so far, they come back together and they form one body. And
so it's like watching a movie backwards, when you see an explosion or something, and then you run the reel backwards, everything then follows back. And you're using the dynamics, the physics of this to see the formation. Okay.
And we found out that Hygiea is, this is known for years now, Hygiea is the parent body of a collisional family, which, and the collision happened 2 billion years ago, a long time ago. Okay. But using mechanical physics, basically, celestial mechanics, we can go back in time and measure this. Asteroids like Vesta or others, which are members of a collisional family, are known to have this irregular shape, potato shape, true, but they also have craters, large craters, like Vesta at the southern pole. On Hygiea, we don't see
later impacts that are being bombarded. Okay.
On Hygiea, we don't see this. We don't see any of those large craters.
Okay. Do you have another image of Hygiea? Let's take a look now.
We have
many images.
Many of them images. In fact, we took around a dozen of those pictures to take advantage of the fact that the asteroid is spinning.
What's its rotation?
13 hours.
13 hours to do a rotation.
And we basically, using the spinning, the rotation, we can see different hemispheres side of the body. And you can see here on the top, those are the observation. No, those are the observations and those are the models. It's all the vice versa. They're so identical that I don't know which one is what now.
So the actual images of the asteroid and computer models.
And computer models, okay. Because we use those observations to build the shape of the body, and that's what we have on the top here, and on the bottom, those are the observations. It looks not that easy because, in fact, we have to take into account the illumination of the sun. And we also use additional data taken by amateur astronomers by occultation to also see, estimate the shape on hemisphere that we can see or we have not seen. So this is a part of the paper and this is analysis, but the true result here is that Hygiea has a shape, a spheroidal shape, the shape that you will expect for a body which has no current strength. So a body which basically is made of very small fragments.
Okay. So we have lots more people coming in. We have Seattle, somebody from Andromeda. That message was obviously sent 2 million years ago, so welcome for being patient. Italy, Japan, Pakistan, Louisiana, St. Ives, Melbourne, and we have a request to identify our speakers. That's you and me, and that's from Ron, which I thought we did at the beginning, but anyway. So I'm Simon.
I'm Frank.
Good afternoon. If you do have any questions, please do send them on, and we'd be very happy to answer them. But if it is from Andromeda, we are not going to wait another 4 million years for that round-trip light signal, because it's Christmas. Okay, so we have this was called identity crisis. We now have this Hygiea. This is an asteroid in the asteroid belt, one of the big ones. It's not a weird potato shape. It's much more spherical than that, and so that brings into account something to do with its classification. And that's something that you're interested in.
Yes.
What is this object? Astronomers love to classify things.
So we love to classify things because it's easier when you communicate with people to tell them what we are being observing. If I tell you this is an asteroid, this is a planet, you will understand. In 2006, we created this new category of body called dwarf planets. Dwarf planets are basically small planets. They have a shape which is close to the equilibrium shape that I mentioned. They did not clear yet the path of their orbit. So bodies like Ceres and Pluto are dwarf planets based on this definition.
Okay.
And they orbit around the sun. Sorry, I should have mentioned that. That's the obvious.
Otherwise,
course.
It's a moon. It's
a moon or it's an exoplanet.
Yes, yes.
That's so in 2006, when astronomers defined this dwarf planet, they gave this definition because the debate at the time was whether or not Pluto is a planet or something else. And since they didn't want to take a decision, I think they created this category called dwarf planets. And now we're realizing that more and more bodies could be part of this category of dwarf planets. And in fact, Hygiea, based on what we see from these observations and the shape modeling and where Hygiea is orbiting around the sun, Hygiea is supposed to be a dwarf planet per the definition of the IAU.
So dwarf planets, as we said, they have to be spherical, so they've hydrodynamically settled into that spherical shape. They have to be orbiting the sun.
And they have not cleared
and they're not cleared their orbit, which is the cryptic one, isn't it?
Yes.
That by clearing orbit means that they haven't quite got the gravitational oomph to be a cosmic vacuum cleaner and wipe out anything else in their orbit.
So if you look at the orbit of Earth or Mars, you will see there is almost no asteroid in orbit in this area, because basically when an asteroid is passing nearby Earth, is pulled by the gravitational field of Earth and will impact Earth. So we have no companion asteroid. We have a few, in fact, but that's another topic of discussion.
Yeah, that's right. That's for 2020.
So in this case, Hygiea has a lot of companions, of course, a lot of asteroids around it. And but Hygiea has the characteristic of the spherical shape that you mentioned. So we are now considering submitting a petition so Hygiea get the official name of a dwarf planet.
Okay. So Pluto's the archetypal dwarf planet, and a dwarf is a good name for these. These are tiny. Obviously, Hygiea is 400 kilometers across, and that doesn't compare with anything else, you know, planet-sized. And so it's a good classification. But it's very different from these weird potato-shaped asteroids.
Yeah. And one of the reasons I kind of like the term dwarf planet, the word dwarf planet, is because something we discover now we are studying more of those dwarf planets, like Ceres with the Dawn mission, Hygiea. We have seen way more now with our program. We are realizing that asteroids are not like these flying rocks, boring, that people were assuming they will be, like this one, for instance. Asteroids are their own geology. They are mini geological world. They have surface processes. If you look at an asteroid, if you look at craters, you will see grooves, you will see flooding in some area, you will see even formation of ice in the case of Ceres, and then the ice melt and flow. You can see moons around asteroids. There is suspicion that some asteroids have in fact ocean underneath the crust, like the largest one, the largest dwarf planet. And recently, even the small asteroid Bennu has this kind of ejection of material. Yeah.
So the closer you look, the more fascinating they become. They develop their own characters. I mean,
like planets.
Yeah, yeah. We do have a question here, and this maybe is quite a broad topic, but do asteroids have any effect on humans? And so we can approach this in a dynamical sense or an emotional sense.
Yes, there are effects on human. The only effect I will think for layman, it will be the formation, the meteors, which are basically small asteroids that come close to our planet and burn into our atmosphere. And some of them become meteorites because they reach the surface of our planet, so forming in some cases, some small craters. Those are the direct effect of asteroids.
Right.
If we're talking about celestial effects, I don't think they have such a strong influence on us.
Yeah. That was from Amal, by the way, that question. Of course, you're right. If these asteroids get too close, some of them aren't permanently in the asteroid belt. Some of them do get closer, and they're called near-Earth asteroids. We have to watch out for those. And that's a whole nother topic of discussion about planetary defense, which we can do a Facebook Live on. There's also ideas to mine asteroids. There's a lot of minerals, and we can talk a little bit more about the chemical composition of Hygiea in a little bit. Got one more question. This is from Ali. How many of such dwarf planets do we have in the bigger solar system, in the solar system as a whole?
So, named dwarf planet, very few. I will say a handful number of them now, dwarf planet officially. But there is a page maintained by an astronomer. We basically started listing the size and shape of asteroids that we know, and you already have a number of 300. But those are made of physical assumptions. It's not made on observations.
Okay.
As I say, we observed 38 of those asteroids so far with this resolution. So we are going to probably see more of those dwarf planets in the future.
Okay. So at the moment it's an asteroid, but you have a campaign, and you're going to take this petition.
We're going to do this.
So how do you petition? Now, the body you go to is called the International Astronomical Union, and that is the only body that is allowed to name astronomical objects. So when you sign off to one of these newspaper articles to have a star named after you, that is fun. Why not? But it's not official. Only the International Astronomical Union can name astronomical bodies and systems and anything.
They can name the surface, features on the surface of asteroids. They can name moons around asteroids, around planets. They name anything in our solar system outside of Earth.
Right. And so how do you petition?
So you write a small proposal. I did that for various moons I discovered in the past. And you justify why you think this should be named dwarf planet, and taking into account basically the definition and showing why Hygiea follow the definition. Then you submit this, and it takes typically between 6 months and a year to get a response from IAU. accepted or rejected, depending. They justify why they're accepted or rejected. They have a commission that meets every 3 months, and they go through some of the requests.
Okay, and that commission presumably is set up of experts in the field,
Experts
so
in
they
the
will
field,
get planetary
from
asteroid experts
everywhere
and
in the world.
so on. Okay.
Yeah.
Okay.
It's an interesting process. I think they're very careful in the way they do that, and it's not an easy task. Because in this case, it's a definition of a body, so it's kind of the answer yes or no. But sometimes they also have to name features on the surface of a body or decide what will be the theme, or sometimes decide the name of a moon. And you know, names can be in English okay, but in a foreign language can be
not okay.
Not okay. So they have to check that as well.
Yes. Yeah.
It's but it's also a good way for the international community to embrace the fact that astronomy is everywhere. I mean, we have names coming from every country in the world now.
Because these objects, you know, as we observe them, this is a global effort. Yeah, astronomy exactly. is an all-inclusive science, and
the sky is for everybody.
Right. Yeah, good. And as soon as this decision is made, it will be announced first, or almost first, on the SETI Institute website. Yeah. So keep a lookout for that. We have another question here. We have, this isn't a question, this is just as Antarctica, exclamation mark. So,
somebody watching from Antarctica?
Somebody is watching it from Antarctica.
It's
lovely,
cool.
Mild summer there now in Antarctica. Yes, yeah, outside in shorts. That's wonderful. So we've got a few minutes left, so if there's any more questions, please do send them in.
I have something I can add about this program.
Yes, please do.
So I mentioned that we have done this with the VLT, the 8-meter class telescope, but astronomers now have new projects. They want to build even bigger telescopes. 40-meter class telescopes. Like one of them is the ELT, which will be the successor of the VLT.
And ELT stands for?
Extremely Large Telescope.
Yes.
And VLT
astronomers
stands for?
have great imagination when it comes to names, but at least you know when you see it, oh, exactly. That's an extremely large telescope. Yeah, so
that will be a
that's accurate.
40-ish meter class telescope, and it will be is being built at the moment in front of the VLT, in another mountain just in front. They can see each other. And this telescope will also be equipped with adaptive optic system.
Okay. Is that pretty standard now? Yeah. Any large telescope will
you
have
cannot build a large telescope without adaptive optic system. It would be kind of a waste. And for this very large telescope, it's mandatory, in fact, for multiple reasons, but you cannot observe without them. Yeah. So imagine now in the future, we're going to be able to get the same kind of pictures for trans-Neptunian objects. The resolution you will get with this extremely large telescope will be good enough to be able to resolve trans-Neptunian objects, to see the shape of some of these dwarf planets, suspected dwarf planet in the trans-Neptunian population, so beyond the orbit of Neptune.
So this isn't just something that's 3 times the distance from the Earth to the Sun, this is 40 times, the distance from the Earth to the Sun, huge distances, and you're looking at something, as we said, roughly the size of a small European country or a US state. That's quite amazing.
And those bodies, when we observe them, like Hygiea with a 30-meter class telescope, you will be able to see details on the surface of Hygiea, like craters, and analyze the surface composition. See basically if there is ice on the surface of this asteroid, for this dwarf planet.
Yeah, that's quite amazing. What just to wrap things up, I think we might have another couple of questions coming in. What is Hygiea made of?
So that's one of the goals of the program, is to measure what we call the density. The density is basically an indication of the composition of the body. Earth has a density of 5, ice has a density of 1. Comets typically have a density between 0.2 to 0.5. Asteroids, we didn't know. We have some measurements coming from various sources, but most of them from asteroids with moons. In this case, there is no moon, but we have now a very good shape estimate, and it's so large that it can also change slightly the orbit of asteroids around it. So we have the mass. So the density is roughly 2 grams cc. So that's twice the density of icy water. It's the same density than Ceres, which is not a surprise because we kind of expected Ceres and Hygiea to be made of the same material. What's interesting here is the density is very low compared to rocks. Rocks have density of 4, 5, 6.
Yeah.
So it's very likely that this body has still a large amount of ice in its interior.
Okay.
He probably formed far away and was captured, like Ceres probably has been formed beyond what we call the ice line. So where there is still a lot of ice and rock, they form together, forming this kind of icy, rocky material. And the body come closer, but it still have the same composition.
Right. It's still far away from the sun that the ice isn't going to
get
evaporate
active,
off
etc.
and everything. So basically a lot of rock, a lot of ice sort of bound together in this gravitational
We will know
ball.
more about those bodies as soon we get samples from Bennu and from Ryugu, because Bennu and Ryugu are two asteroids of the same classification, C-type, C-class asteroids.
C for carbon. So
C
sort
for
of,
carbon, yeah, because they're extremely dark. And those missions, the Hayabusa 2 for Ryugu and OSIRIS-REx for Bennu, will basically bring samples of those asteroids. For the first time, we're going to have pristine samples coming from C-group asteroids. The first thing we're going to do is to look at those small fragments and see the amount of ice and see the amount of rock to truly understand where they form.
Because it's quite possible these are pristine remnants. These are like the sort of building blocks of the solar system.
Yes.
It's like going to a new housing area and picking up the bricks that haven't been incorporated into the houses. It's what's left over from the construction of the solar system.
Exactly.
And that's very, very exciting indeed. Okay, we wrap this up with one last question maybe. Do we expect to find Tecna signatures on asteroids? And that is from Ancient Cyborgs and Robots. So I'm pleased that we have a non-humanoid audience here. We are all inclusive at the SETI Institute.
So,
Tecna signatures.
So people have been thinking about how we could basically use asteroid to build a civilization. And one of the idea will be in the future where we will have the technology, we will start mining asteroid probably, we will have to live there. And what people will do is probably to extract the material from the inside of the asteroid and live inside the asteroid. Why do you want to live inside an asteroid? Well, because you're gonna get protected from solar radiation, for instance. That will be a natural way to protect yourself from the bombardment of the sun. So that will be a way for civilization to have a stable environment in space that they can easily access and live in. How are we going to detect this civilization inside an asteroid? That's a very good question. In fact, if there is aliens now living inside an asteroid, I'm not sure we'll be able to detect them by simply looking at the asteroid.
Right, that's interesting. So as a remote outpost for the Andromedans who are listening in today, that's a possibility. Thank you very much. We will wrap it up there. Thank you, Franck,
Thank you
very much indeed.
Simon.
Thank you to everybody who listened in today. We hope you have a wonderful holiday break wherever you are and whichever continent or planet or galaxy you are in. And we will see you again in 2020.